We know it's degenerate in some way, but we don't know what type of point it is. Okay, so that's actually what you need to remember if you're formula-oriented. That's all you need to remember about today. But let's try to understand why, how this comes out of what we had there. Okay, so I think maybe I actually want to keep... So maybe I want to keep this middle board because it actually has, the recipe that we found before for the quadratic function. So let me move directly over there and try to relate our old recipe with the new one. Okay, you're easily amused. Okay, so first let's check that these two things say the same thing in the special case that we were looking at. Okay, so let's verify in the special case where the function was ax squared plus bxy plus cy squared. So, well, what is the second derivative with respect to x and x? If I take the second derivative with respect to x and x, so first I want to take maybe the derivative with respect to x. Let's take first the first partial, w sub x. That will be 2ax plus by, right? So w sub xx will be, well, let's take the partial with respect to x again. That's 2a. W sub xy, I take the partial with respect to y, I will get b. Okay, now we need also the partial with respect to y. So w sub y is bx plus 2cy. In case you don't believe what I told you about the mixed partials w sub yx, well, you can check, and it's again b. So they're indeed the same thing. And w sub yy will be 2c. So if we now look at these quantities, that tells us, well, big A is 2 little a, big B is little b, big C is 2 little c. So AC minus B squared is what we used to call 4 little AC minus B squared. Okay? Ooh. So now you can compare the cases. Well, they're not listed in the same order, just to make it, harder. But so we said first so the saddle case is when AC minus B squared in big letters is negative. That's the same as 4AC minus B squared in lowercase is negative. The case where capital AC minus B squared is positive, local min and local max, corresponds to this one. And the case where we can't conclude was what used to be the degenerate one. Okay, so at least we don't seem to have messed up when copying the formula. Now, why does that work more generally than that? Well, the answer to that is, again, Taylor approximation. Okay. So let me just do here quadratic approximation. So quadratic approximation tells me the following thing. It tells me if I have a function f of xy, and I want to understand the change in f when I change x and y a little bit. Well, there's the first order terms, there's the linear terms that by now you should know and be comfortable with. That's f sub x times the change in x. And then there's f sub y times the change in y. Okay, that's the starting point. But now, of course, if x and y, if we're at a critical point, then that's going to be 0 at a critical point. So that term actually goes away. And that's also 0 at the critical point. So that term also goes away. Okay, so linear approximation is really no good. We need more terms. So what are the next terms? Well, the next terms are quadratic terms. And so, I mean, if you remember the Taylor formula for a function of a single variable, there was the derivative times x minus x0 plus 1/2 of the second derivative times x minus x0 squared. And see, this side here is really Taylor approximation in one variable, looking only at x. But of course, we also have terms involving y and terms involving simultaneously x and y. And these terms are f sub xy times change in x times change in y plus 1/2 of fyy times y minus y0 squared. There's no 1/2 in the middle because, in fact, you would have two terms, one for xy, one for yx, but they're the same. And then, if you want to continue, there's actually cubic terms involving the third derivatives and so on, but we are not actually looking at them. And so now, when we do this approximation, well, the type of critical point remains the same when we replace the function by this approximation. And so we can apply the argument that we used to deduce things in the quadratic case. In fact, it still works in the general case using this approximation formula. So the general case reduces to the quadratic case. And now you see actually why, well, here you see again how this coefficient, which we used to call little a, is also 1/2 of capital A. And same here, this coefficient is what we call capital B or little b, and this coefficient here is what we called little c, or 1/2 of capital C. And then when you replace things into the various cases that we had here, you end up with the second derivative test. So what about the degenerate case? Why can't we just say, well, it's going to be a degenerate critical point?